Chapter 2 covers fraction notation, and the first major parts are multiplication and division. So section 2.1 covers the following topics. We determine whether one number is a factor of another number, and then we're going to find multiples of a number and determine whether a number is divisible by another. And given a number from 1 to 100, we determine whether it is prime, composite, or neither. And then the last part of section 2.1 would be to find the prime factorization of a composite number. That turns out to be quite important, as you will see. So the first topic will be about factorizations, and so we talk about factors. And so if we consider only the natural numbers, 1, 2, 3, etc., if we look at the product, 3 times 4 equals 12, then we say that 3 and 4 are factors of 12. Because when we divide 12 by 3, we get a remainder of 0. So we say the divisor 3 is a factor of the dividend 12. Okay? So this will become more important later on, but right now that is all we were going to talk about here right now. And so here is how we determine if a number is a factor. In the product A times B, A and B are called the factors. If we divide Q by D, in other words, Q is a quotient, is a number, by a number D, and get a remainder of 0, then the divisor D is a factor of the dividend Q. So let's think about that again. So we have a number, Q, the quotient, divided by D, divisor, and we have a remainder of 0, then the divisor D is a factor of the dividend Q. And we're going to go over some examples here in just a moment. For example, exercise number 1 asks us if 8 is a factor of 72. Well, when we divide 8 into 72, we know that's equal to 9. That's a remainder of 0. So here the answer is yes, 8 is a factor of 72. In the second example, 2,384 and 28, when we divide 28 into 2,384, we get 85 and the remainder of 4. So therefore, 28 is not a factor of 2,384 because there's a remainder of 4 when we do this division. Next, we're going to consider factorization. For example, we say that 12 equals 3 times 4, so we can say that 3 times 4 is a factorization of 12. But that's not the only one. For example, 6 times 2 is 12, 12 times 1 is 12, and 2 times 2 times 3 is 12, and 1 times 3 times 4 are also factorizations of 12. And since a equals a times 1, every number has a factorization, and every number has factors. For some numbers, the factors consist only of the number itself and 1. For example, the only factorization of 17 is 17 times 1, so the only two factors are 17 and 1. So next we have some exercises by listing all the factors of each number. Well, if 1 is certainly a factor, it's a factor of any number. And since this is an even number, 2 is a factor. And since 10 is divisible by 5, 5 is a factor. and 10 is divisible by 10, so 10 is a factor. So with smaller numbers, that's pretty easy to do. For the next example, number 4, 1 times 45. So 1 is a factor. 2 is not a factor because it's an odd number. But 3 times 15 is 45. So 3 is a factor. 4 is not a factor. It's not an even number. And 5 times 9 is 45. So 5 is a factor. And 6, 7, 8, and 9 are not factors of 45. 6, 7, and 8 are not. And 9 is already listed. So therefore, the factors of 45 are 1, 3, 5, 9, 15, and 45. Next, we're going to look at example 5. So for the number 62, certainly 1 is a factor. And since this is an even number, 2 is a factor. And since 2 times 31 equals 62, 31 is a factor. And of course, the number itself is also a factor because we can write it as 1 times 62. So these are the factors of 62. The next example is the number 24, number 6. And so here, 1, of course, is a factor, and 2, because it's an even number. And we know 8 times 3 is equal to 24, so 3 is a factor. And we know 6 times 4 is 24, so 4 is a factor. And that also makes 6 a factor. And since 3 times 8 was a factor, we know that 8 is a factor. And 2 times 12 is 24, so 12 is a factor. And 1 times 24 is 24, so 24 is a factor. So these are then the factors of the number 24. Next, we talk about multiples and divisibility. And so a multiple of a natural number is a product of that number and some natural number. For example, some multiples of 2 are 2, because 2 equals 1 times 2. 4 is a multiple of 2 because 4 equals 2 times 2. And 6 is a multiple of 2 because 6 equals 3 times 2. 8 is a multiple of 2 because 8 equals 4 times 2, etc. So many more multiples of 2's, of course. So we find multiples of 2 by counting by 2's. 2, 4, 6, 8, and so on. So now we want to do some exercises related to this idea of multiples. And so show that each of the numbers 5, 45, and 100 is a multiple of 5. Well, 5 we can write as 1 times 5. So that's a multiple of 5. And we can write 45 is equal to 9 times 5. So it is a multiple of 5 also. And we can write 100 as 20 times 5. Again, it's a multiple of 5. The factor being 20 in this case. Similarly, for exercise number 8, show that each of the numbers 10, 60, and 110 is a multiple of 10. Well, 10 is equal to 1 times 10. That's a multiple of 10. 60 is equal to 6 times 10. That's a multiple of 10. And 110 we can write as 11 times 10. Again, it is a multiple of 10. The multiplier in this the factor is 11. So these are pretty simple exercises, and I hope that you find that's very easy for you to do also. Number 9 asks us to find 10 multiples of 10 by multiplying number 5, by multiplying to find 10 multiples of 5. So multiplying 1 times 5 is 5. Multiplying 2 by 5 gives us 10. Multiplying 3 by 5 is equal to 15. And 4 times 5 is 20. And 5 times 5 is 25. And 6 times 5 is 30. And 7 times 5 is 35. And 8 times 5 is 40. And 9 times 5 is 45. And 10 times 5 is 50. Okay? So it's easy to find multiples of a number. Here's the 10 multiples. Again, to review, this was 1 times 5 equals 5. That's 2 times 5 equals 10. 3 times 5 equals 15. 4 times 5 equals 20. And then 5 times 5 equals 25. 6 times 5 equals 30. 7 times 5 equals 35. 8 times 5 equals 40. 9 times 5 equals 45. And 10 times 5 equals 50. Next topic is divisibility. We say a number A is divisible by another number B if there exists a number C such that A equals B times C. The statements A is divisible by B and A is a multiple of B and B is a factor of A all have the same meaning. In other words, they're all equivalent. Okay? So again, the statements A is divisible by B, or A is a multiple of B, or B is a factor of A, all have the same meaning. So we can express divisibility in 3 different ways. For example, 27 is divisible by 3 because 27 equals 3 times 9. We can also say that 27 is a multiple of 3 because, 9 times 3 is 27. And 3 is a factor of 27. You can see it in this statement here. Okay, so number 10 asks, determine whether 16 is divisible by 2. So we do long division, and so we divide 8, or 2 rather, into 16. That's 8 times. 8 times 2 is 16. We subtract, so the remainder is 0. And since the remainder is 0, 16 is divisible by 2, since the remainder is 0. In exercise number 11, we are to determine whether 125 is divisible by 5. So we simply divide 5 into 125. So 5 goes into 12 2 times. So 2 times 5 is 10. Subtract that, we get a 2 to bring down the 5. And 5 goes into 25 5 times. And so 5 times 5 is 25, we subtract. So the remainder is 0. And since the remainder is 0, we can conclude that 125 is divisible by 5. So the answer is yes. Again, because the remainder is 0 when we divide 5 into 5. In exercise 12, we are asked to determine whether 125 is divisible by 6. So we do the same thing. We divide 6 into 125. So 6 goes into 12 two times. So 2 times 6 is 12. We subtract. It's 0. We bring down the next digit. That's 5. And 6 goes into 5 0 times. So 0. You bring down. So then 0 times 6 is 0. And we subtract, so we have a remainder of 5. So in other words, 20, remainder of 5. And because it's a remainder, 125 is not divisible by 6. If you use a calculator, if you divide 125 by 6, so when you use the calculator, 125 by 6 is 20.83333, continuing indefinitely. So it's 20, and this indicates that there's a remainder. If we do it in long division, then we get the exact number, what the remainder is. Next is a very important topic called prime and composite numbers. A natural number that has exactly two different factors, only itself and 1, is called a prime number. So that's the definition of a prime number. Okay? So it has exactly two different factors, only itself and 1 is called a prime number. For example, the number 1 is not prime because the only factors are 1 times 1 and they're not different factors. And then the next statement is a natural number other than 1 that is not prime is composite. The natural number other than 1 that is not prime is called composite, or a composite number. So the next few exercises deal with prime and composite numbers. And so let's look at these numbers. So we have the numbers are 1, 2, 6, 12, 13, 19, 41, 65, 73, 99. So the numbers that are prime are 2, 13, 19, 41, and 73. So the prime numbers are 2, 13, 19, 41, and 73. And by the way, on page 89, on top of upper right-hand corner are the prime numbers from 2 to 97. So you can look it up. And then the composite numbers are 6, because 6 can be written as 2 times 3. 12, because 12 can be expressed as 2 times 6. And 65, because that's equal to 5 times 13. And 99 is a composite number because it's 3 times 33, or 9 times 11. So there's more than one factorization sometimes. And then the number that's neither composite nor prime, well, that's the number 1. Remember, 1 is not a prime number, and it's not a composite number either. So that's the one that's neither prime nor composite. Another important topic is that of prime factorizations. So when we factor a composite number into a product of primes, we find its prime factorization. So to do this, we consider the primes 2, 3, 5, 7, 11, 13, 17, and so on, and to determine whether a given number is divisible by the primes. So we do some exercises on how to do that. So first of all, here's the table of prime numbers from 2 to 97 that I mentioned. That's on page 89 in the upper right-hand corner. And then here, using your calculator, for each pair of numbers, determine whether the second number is a factor of the first number. So when you use your calculator and you divide 502 by 8, you find there's a remainder. So 8 is not a factor of 502. It is not, because 502 divided by 8 is equal to 62.75. So in other words, there's a remainder there. And when we divide 651 by 21, that is yes, because 651 divided by 21 is equal to 31 with no remainder. And when we divide 3,875, let me just do over here, 3,875 by 25, that's equal to 155 without a remainder, so that's also, the answer is yes. In other words, 25 is a factor of 3,875. And for the last one, number 4, when we divide 1,047 by 14, that gives us 74.785, and that is rounded, 785. That number is rounded, a few more decimals. And so since there's a remainder there, 14 is not a factor of 1,047. Here's an important observation. Every number has just one prime factorization, in other words, a unique prime factorization, other than the order in which you list the factors. But since multiplication is commutative, the order of the factors is not relevant. And there are many different ways to determine prime factorization of a number. And let me show you one that's very easy to do. It's called the tree method, and you can use that for many, many numbers. So the way it works is that you write down 72. Now you know it's an even number, so you can write it as 2 times 36. Now 36 is an even number also. We can write it as 2 times 18. And 18 is an even number, so we can write that as 2 times 9. And 9 we can write as 3 times 3. So then the prime factorization of 72 is equal to 2 times 2 times 2 times 3 times 3. So here are the prime factors. Or we can write it as 2 to the third power times 3 to the second power. Either way. But again, there's only one prime factorization. For instance, if we started it in a little different way, if we started the prime factorization of 72 in a different way, for example, 72 we can write as 2 times 36. Now 36 is an even number, so we had that already. We can write that as 4 times 18. And we can write 4 as 2 times 2. And 18 we can write as 2 times 9, and we can write 9 as 3 times 3. And so as you can see, the factorization is the same. 2 times 2 times 2 times 3 times 3. So either way, no matter how you start the factorization process, the end, the prime factorization, will always be the same. And here's a little note of caution. And that is to keep in mind the difference between finding all the factors of a number and finding the prime factorization of a number. For example, here, the prime factorization of 72 is 2 times 2 times 2 times 3 times 3. On the other hand, the factors of 72 are these: 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72. So remember the difference. What the prime factorization is, in other words, factors of prime numbers. But the factors of 72 are, in some cases composite numbers like 6 and 8 and 9, 12, etc. Okay? So be sure to keep that difference in mind. So the next few exercises is about finding the prime factorization of various numbers. So when we look at number 14, the number 6 has a prime factorization of 2 times 3, so it's equal to 2 times 3. The prime factorization of 12 can write as 2 times 6, and 6 is 2 times 3. Two times 3. So the prime factorization of 12 is 2 times 2 times 3. The prime factorization of 45. The 45 we can factor as 5 times 9. And 9 we can factor as 3 times 3. So then the prime factorization of 45 is 3 times 3 times 5. And when we look at the prime factorization of 98, let's see, we have space for that here. Yeah, we can do that. So for 98, number 17, we can write that as a factor that's 2 times 49. And 49 is equal to 7 times 7. So therefore, the prime factorization of 98 is 2 times 7 times 7. And by the way, it's kind of common to write the factors in increasing order. It's, the smallest numbers to the left, and then they increase in magnitude. So for number 18, we have the number 126. So that's number 18. And let's do the prime factorization of 126. So we can factor this in 2 times 63. And 63 is 9 times 7. And 9 is 3 times 3. So therefore, the prime factorization of 126 is equal to 2 times, is it 2? 3 times 3 times 7. Similarly, when we look at number 19, the number 144, let's find the prime factorization of 144. So it's 2 times 72. And 72 is equal to 8 times 9. And 8 can be written as a factor of 2 times 4. And 4 can be written as a product of 2 times 2. And of course 9 is 3 times 3. So therefore we have the following prime factorization of 144. 2 times 2 times 2 times 2. So 2 times 2 times 2 times 2 times 3 times 3. Maybe you want to remember this as a little memory trick to underline the factors that you've counted already by underlining them, so you don't get confused which one you've already accounted for. So that's a prime factorization of 144. And of course you can always check your answers with a calculator, which is something I'd really recommend. So, okay, then we have number 20. Number 20 asks us to find the prime factorization of 1960. So let's do that. 1960. So that's 1960 is 2 times 980. And we can factor in 2 times 490. And that can be written as 2 times, let's see, 245. And that's equal to 7 times 35. And 35 is a product of 5 times 7. So therefore, the prime factorization of 1960 is 2 times 2 times 2. So 2 times 2 times 2 times 5. There's 1 5 there. Times 7 times 7. And the other exercise, number 21, was to find the prime factorization of 1925. So I can divide 5 into 1925. So it's 5 times 385. And I can divide 5 into 385. And that's 5 times 77. And 77 is a product of 7 times 11. Therefore, the prime factorization of 1925 is 5 times 5 times 7 times 11. So prime factorizations happen quite frequently. You'll be asked to do that. There are many instances in the future where we will resort to prime factorizations for many different reasons. So be sure you learn thoroughly how to do that. And as always, there are additional drill exercises in the section 2.1 exercises in the exercise set on pages 91 and 92. And I'd really recommend you practice your prime factorization skills and other skills as well, like finding the factors of a number, etc. This is probably not sufficient, but at least it got you started. Okay? So this now concludes section 2.1.